Assalamu alaikum.
Walaikum salam.
Walaikum assalam.
So section B, we have completed discussion on balance steel ratio, and with other sections I have also completed the discussion on remaining slides, and I can share videos. Today's lecture I will also record and it will be uploaded, so few slides are left in today's lecture, and then we can discuss the next presentation on how to design the cross section. So I finished discussion on this slide where we checked that our example problem rho was 1.36% and rho balanced we got for the concrete grade of 20 and steel 300 megapascal, rho balanced of 3.2%. So in this way I mentioned that this unique reinforcement ratio is about crushing in concrete and yielding of steel bars in a cross section simultaneously. So this is the dividing line between the under reinforced, tension controlled and over reinforced behavior. So if rho will get bigger than rho balanced, we will be in the over reinforced domain, and less than rho balanced we are in the tension controlled domain. So this information is very useful to classify the cross section. Now furthermore, we have few more important type of cross sections with respect to flexure at ultimate load levels, which we want to discuss today. So let's start recording. So at the moment 26 students are online. Okay, now this tension control section is one which will be showing at the cross section at ultimate load against crushing of concrete 0.003. Steel will be at either equal to or greater, okay, either equal to or greater than 0.005. So actually if you compare it with balance reinforced, it was that epsilon s will be exactly equal to epsilon y. Now this is another behavior that when concrete will approach failure, steel at that stage will be at a quite big strain, which is 0.005. So it must be on yield plateau, well above yield strain, and even above that it may be 0.008, 7, 7, 9. So it shows a ductile cross section. So if I draw a strain diagram corresponding to this condition, that 0.003 versus 0.005 as the shown on right hand side, I can write from similar triangles this equation: 0.003 over C is equal to 0.005 over D minus C. And when I simplify, I get a very useful expression that neutral axis depth will be then 3/8 of the effective depth of the cross section. So all neutral axis depths equal to 3/8 of effective depth or less than this will reflect that the cross section is ductile, it is tension controlled, under reinforced. So when you will keep on decreasing the neutral axis depth, it means your strains in steel are getting bigger and bigger. So all C's equal to or less than 3/8 of the effective depth will show that cross section is tension controlled under reinforced. And this neutral axis depth we are going to use in our various derivations because this is very important depth, and we can calculate from C A because we have the relationship developed between A and C, which is A equal to beta 1 C. So I will multiply C with beta 1 and I can get the Whitney's uniform stress block depth. So all A is less than or maximum a guarantee that cross section will be at 0.005 or bigger strain corresponding to crushing in the concrete. Now, in addition to this classification, there is one more domain which is very much important, and we in classification of cross sections we may get a situation that cross section is above yield strain but it is below 0.005 in steel corresponding to crushing in concrete. So it is termed as transition domain. So it means when I will draw the cross section strain, I will have the same linear strain diagram and I can derive the equation. So corresponding to this, when I will put some strain value over here, for example, if the cross section is reinforced with grade 420 steel, then the yield strain of grade 420 steel is 420 over modulus of elasticity. So it will be 0.0021 for grade 420 steel. So if I have a cross section which is reinforced with grade 420 steel, but the steel at the crushing of concrete, if suppose it is at 0.003. So concrete is also at 0.003, which is the failure limit, and steel at that instant was also at 0.003. So it means epsilon s is greater than epsilon y, which is 0.0021, but it is less than 0.005. So in a way, we can then state that when I will calculate the C value using this strain diagram, obviously I will get C greater than 3/8 D, and corresponding A will be also greater than beta 1 into 3/8 D. But you will agree that since we are saying epsilon s although is less than 0.005, but it is greater than epsilon y. So when it is equal to epsilon y, C becomes C equal to CB and A becomes A equal to AB. So since our transition domain is that it is greater than yield, so I have no ambiguity in writing that C will be less than C balanced, or A will be less than A balanced as mentioned underneath. So it is such a domain in which A or C will be greater than the A or C of 0.005 tension control section, but the C or A will be less than the balanced CB or AB. So it will be in between this range. For such transition sections, they are to be considered for ultimate stand design by selecting phi value, capacity reduction factor between 0.9 to 0.65. So if the cross section is at 0.005 for bigger strain, phi will be 0.9. If the cross section is balanced or it is in over reinforced domain, rho greater than rho balanced or rho equal to rho balanced, phi will be 0.65, strict reduction. But if epsilon s is less than 0.005, but it is greater than epsilon y, then we need to interpolate the phi between 0.9 and 0.65, and we will be using strain in the steel bars. Linear interpolation will be done to determine the phi value. So that we are going to discuss on next slide, how we will determine the phi for such transition reinforced cross sections. In addition to this unique strain diagram, there is one other strain magnitude in the cross section which was considered important in 2011 or previous publications of ACI. This section was considered one other additional section which has the strain in the steel at 0.004 corresponding to crushing in the concrete. But in latest ACI publication 2019, this section of the transition domain is not given too much highlight or importance. So, but the same thing we can evaluate that a strain diagram will then be corresponding to crushing steel at 0.004, and against this strain diagram we can write the equation and we can get C. So for such cases C will become 3/7D. So obviously it will be little deeper than 3/8D because 3/8D will be little shallower than this because strain will be 0.005 corresponding to that crushing in concrete. So finally we can then comment that for all cross sections with rho less than rho balanced, which was our case of example problem, rho was 1.36%, which was well below rho balanced of around 3%. All such cross sections are called under reinforced tension controlled cross sections. And within the under reinforced cross section, since rho is less than rho balanced, there also comes transition controlled cross sections. So in under reinforced cross sections where rho is less than rho balanced, we further have two domains: tension controlled cross sections in which strain will be 0.005 or bigger, and transition controlled sections in which strains are greater than epsilon y but less than 0.005. So all tension controlled or transition controlled sections are also named as under reinforced cross section. Don't get confused with the word under. Under does not mean they are under designed or they are weak. It is the you can say classification of the cross section which is ductile, which will give us warning before failure in terms of offensive sag, distress, cracking, and then after all this warning, finally the crushing in concrete and failure will take place. It is always desirable that a section is under reinforced, otherwise failure will be initiated by crushing in the concrete first. As concrete is a brittle material, so this failure will be sudden, which is undesirable. We want that steel should yield first. It should yield excessively, give us warning in terms of sag and cracking on the beam soffit if the beam is sagging, and then finally crushing of concrete will take place. Failure should not be initiated by all of sudden crushing in concrete while steel is still in the elastic domain, because such cross sections are not ductile. They will not absorb much energy before failure, and they will give us less warning. So in new design, we will not put our cross sections in even at balanced or in over reinforced domain. We will put them in the domain of tension control, where epsilon s will be greater than or minimum equal to 0.005. However, in capacity analysis, in review of the existing design, you may come across some unwanted designs where you get the impression that corresponding to crushing in concrete, steel is not yielding. We classify them as compression controlled or over reinforced sections. So the section in which steel strain in extreme tension steel is less than its yield strain, while concrete approach its crushing. So it means such cross sections will not fully utilize the steel strength, because steel is in the proportional limit while concrete crushed. Such cross sections will give us less warning. And in terms of neutral axis depth, we have now the understanding that C will be greater than balanced neutral axis depth in such cross sections, and uniform stress block depth will be greater than the balanced cross section uniform stress block depth. As I mentioned earlier, that if section is tension controlled with epsilon s 0.005 or bigger, phi will be 0.9. And if the section is compression controlled, it means epsilon s is equal to epsilon y, or epsilon s is less than epsilon y, phi will be 0.65. In columns, which will be our topic in next semester, in some cases we will be having the compression members which are confined by the spirals, continuous helically wound spiral steel. So in such case, ductility will be better than discrete rings, ties, which are enveloping the longitudinal bars. So if the member is compression controlled, but it is confined by spiral steel, then code will relax this 5, and rather than 0.65, you will be allowed to use 5.75. So it means 25% reduction on capacity, rather 35% as in case of the compression controlled cross sections with ties. However, in case of transition reinforced cross sections, phi will be linearly interpolated between 0.65 to 0.9, or if they are spiral reinforced, 0.75 to 0.9. How we will do this linear interpolation to determine phi for such transition reinforced cross sections? So this picture will help you to do that linear interpolation. For all cross sections with epsilon s less than epsilon y, phi will be 0.65. And for all cross sections with epsilon s greater than or equal to 0.005, phi will be 0.9. But for such cross sections in which we have the epsilon s greater than epsilon y but less than 0.005, we need to determine the phi. And in order to determine the phi, we want slope of this line, because we can add 0.65 fixed phi, and then the additional height we can determine that will be added up here to get the final phi value. Now the slope of this line is actually difference 0.9 minus 0.65, which is 0.25, divided by the difference in base 0.005 minus epsilon y, which is over here, and then I will multiply this slope with the epsilon s, which I will get from the analysis that how much is the steel strain. As I have given you example that suppose the steel strain is 0.003. So that 0.003 will be with respect to this up to this. But since I want to get the distance from this up to this to get this height, so I will subtract from epsilon s, which is given notation here, epsilon with subscript t. So epsilon t minus epsilon y. So it means 0.003. Suppose if my steel has the strain 0.003 and the grade was 420, so it means 0.0021. So this will become the base into the slope. I can get phi. So just for practice, if I use the same equation, I will say 0.65 plus 0.25 over 0.005 minus what is epsilon y. For grade 420, it is 0.0021. So this will give me slope into, since I have given you example that steel strain, if it is at 0.003 minus epsilon y, which is 0.0021. So for such cross section, what will be phi? Can you please use your calculators and tell me what will be the phi value? Please. Anyone?
0.73.
Good. 0.73. So in this way, we can determine the phi. Underneath for spirals, they are giving you another equation. Now it will start from 0.75 and the difference will also be 0.9 minus 0.75, so it will drop to 0.15. So 0.15 over base will give us slope, and then the same abscissa we will calculate and multiplied with the slope to get the phi value. So in this way, we are going to apply this this equation to determine phi when we are dealing with the transition reinforced cross sections, and we want to apply capacity reduction factor for such cross sections. Now, in the discussion we made on cross sections, I have drawn one row scale in which the maximum row was row balanced, and the minimum we are going to discuss on next slide is row minimum. And we, in our example problem, had reinforcement ratio 1.36%, while row balance was close to 3%. I recall 3.2% or something like this. Now, we want to know that our cross section has the reinforcement ratio above row minimum, because this is the lowest limit, and below this row minimum it will be dangerous, because section will fail suddenly by fracturing of the steel bar, and wide cracks can appear if row will go below row minimum. Above row balance also undesirable. But as I have given you one strain diagram for tension controlled under reinforced cross section, that corresponding to crushing in the concrete, steel is at 0.005 or bigger. So this is very ideal behavior, that we have lot of ductility warning before failure. So corresponding to this strain diagram, if I can determine a rho value in the cross section, because corresponding to balanced failure, which I derived in last lecture, we had a strain diagram that epsilon y will be corresponding to crushing in the concrete, and corresponding to this diagram we got rho balanced from derivation. And in this case, which is another desirable section, the rho what we will calculate will be rho with the subscript max. So this max means that maximum allowed reinforcement ratio. So all rows equal to or less than rho max will give us strains in corresponding to crushing in concrete greater than or equal to 0.005. So rho max will fall somewhere over here. Very desirable behavior. So first thing is, we want to derive rho max equation, and then we want to check that our example beam has the rho less than rho max or greater than rho max. Although we have calculated in that example problem that our epsilon s was at 0.007, I remember it was 0.007 or bigger. So it shows that steel is above 0.005 corresponding to crushing in concrete. So it means we will be in this domain less than rho max, and if furthermore our rho is greater than rho minimum, we will classify our example beam that it is in the ideal domain. However, if rho comes out to be greater than rho max but less than rho balanced, we will be in the transition domain. Still, it is under reinforced but less preferred because phi will get bigger value and phi will get value less than 0.9. So conductivity will also be less as compared to this domain. So this is ideal domain. And this is undesirable above rho balanced. Let's find out first that can I derive equation for rho max like I did for rho balanced. I will take the help of again equilibrium equation T equal to C. For all derivations, I will take help from the only unique equilibrium equation for flexural members, that is at section we have longitudinal equilibrium and sigma fx equal to 0, so T equal to C, and also will take help from the strain diagram because strain diagram will give us substitution in the equation for the condition which we are desiring, that for example in this case we are desiring to substitute in the equation that neutral axis depth which will provide us 0.005 versus crushing in the concrete. So starting from T equal to C, I will put T as ASFY. Since section is under reinforced, there is no ambiguity regarding yielding of the steel. So I can confidently put Fs equal to Fy. Then Whitney's uniform stress block depth theory and multiplying the uniform stress with the cross section on which it is present A into B, I can get the components of T equal to C. Then I will replace area steel with the rho because we know that area steel over effective area in flexural members, this ratio is reinforcement ratio AS over BD. So I replaced AS with rho BD, and then I brought rho on one side like I did in derivation of rho balanced. If you recall, in rho balanced we did the same exercise. So we brought rho on one side and all other variables on the right hand side, and we put B as subscript under the A and rho, just to signify that this derivation we are doing for the balanced reinforcement ratio. Now in this case we are doing the same thing, and we are keeping rho on one side and all other variables on the right hand side, and we are getting the same terms: 0.85 ratio of strengths A over D. Now in order to put subscript max over here, I should select that unique uniform stress block depths which gives me epsilon s equal to 0.005. So in order to put max over here, I will take help of the strain diagram that corresponding to crushing in concrete steel is at 0.005. And just few minutes ago, we have derived this from the strain diagram and we got C equal to 3 over 8D and A equal to beta 1 3 over 8D. So this we can use as A max because it is such a uniform stress block depth, which ensures 0.005 in steel corresponding to crushing in concrete. So I just replaced this A with A max. So once I'm putting this A, I'm allowed to use max as subscript. So when I put this A, this D and this D will cancel. So I will get a simplified shape of rho max 0.85 ratio of material strengths into 3/8 beta 1. So for concretes of lower grade, beta 1 is 0.85. So it means 0.85 beta 1, it will become 0.85 square into 3/8 into Fc prime over Fy. So I suggest you to memorize these useful expressions, rho balanced as well as rho max. So these are very useful expressions and you are going to use them quite frequently. So please keep them in mind rather than always consulting the design aids. And also keep in mind the simple derivations, how we derived them. So with this information now, if I ask you that our beam, example beam, with the known material grades, can I calculate rho max? We had 0.85. Our beta 1 is also 0.85 because concrete grade is 20 into 3/8 into 20 over 300. Our steel grade was 300. So can you give me rho max of cross section? Point 0.85 square, 3/8, 20 over 300. So let me convert it into percent. So it is 1.8%. I will multiplying with 100. So it means rho max is 1.8%. So we rightly got the epsilon s greater than, so good. We rightly got epsilon s greater than 0.005 because its classification based on rho is also revealing that rho in the cross section is less than rho max. So our rho was 1.36% while rho max is 1.8%. So we have no objection in using phi then 0.9. And this is quite useful classification that rather than going into detailed analysis right in beginning, if we determine rho max, rho balanced, and even rho minimum, and we compare them against rho of the cross section, we can classify the cross section within few minutes. And in this way, we can comment without going into detailed analysis that what type of cross section it is. Now, out of this discussion, rho minimum is only left. What is rho minimum? For rho minimum and for transition sections, we, as I mentioned that in previous course, versus 0.003, epsilon s 0.004 was also one strain magnitude which they suggested to calculate And against that, again, the rho derivation of rho was that rather than 3 over 8, you will get 3 over 7. But in the latest code, there is no such, you can say, uh, assessment required. So you can even ignore this calculation. As per latest code, I will tell you on the last slide that what in latest code they are suggesting to classify the cross section. So we will keep in mind rho max, rho balanced, and rho minimum. And I am stating rho max as the rho corresponding to 0.005 in steel and 0.003 in concrete. So this we can ignore because still we are able to classify our cross section and we are in the safe limit. Now, in the latest 2019 publication in chapter 9, empirical equations are given to determine rho minimum in the cross section. As I said earlier, that once modes of rupture will come, section will get cracked. You are studying in allowable stress design, uncracked section, then cracked transform section. So when section is uncracked, it means concrete is intact, but the instant section will be cracked, modes of rupture will come. Concrete will not take any more tensile stress, while all the stresses will be transferred to the steel. So steel must take on that stresses. If the steel ratio in the cross section is too low, what can happen? The instant modes of rupture comes and shift of stresses is now entirely on the steel. Steel at the same instance may fracture. So that will be more dangerous, that wide cracks suddenly appeared and section collapsed. So the minimum steel is always provided in structural members because when concrete is cracked, then load comes on steel. So there should be minimum amount to resist that load to avoid sudden failure. But keep in mind that this formula is not for slabs. So for when we will discuss design of slabs, we will be giving you one other rho minimum requirements. Only for beams this is valid. So there are two equations which we want to check, and out of them larger will govern. Now in our example problem, these questions are based on test results. In our example problem, FC prime is 20 and Fy is 300. So what will be the answer from left equation and then from the right equation? Can you tell me? Please determine. 20 under root divided by 4 into 300. Good. So you are multiplying it with 100 to get in percent. So 0.4. Please repeat. 0.4. Sorry, 0.37. And what you get from right side equation? Good. So 0.37% and 0.443, right? 4.467. Let it be 0.48, right? 0.48. So we can truncate it to second decimal place, 0.48. So it means 0.48% minimum reinforcement ratio will control. So we are happy that our beam has the reinforcement ratio well above 0.48% and even below rho max, and it is in the under reinforced tension control domain. 5 we can use 0.9, so this capacity analysis will be useful to determine the capacity of that cross section. Just for your understanding, for example, if in the same example problem I have given you 3 bars, number 25, if I just increase the layers and I mention that there are 2 layers of steel and each layer has 3 number 25 bars, so it means in the same cross section you will get 6 into 510. So 6 into 510, then divided by 300, which is B of the cross section, and even effective depth will also change. With 2 layers it will further get shallower. Earlier we used effective depth by subtracting cover of 75 millimeter from 450, so we use the effective depth 375. But when you have 2 covers, the centroid of the steel will further move up, and because there are 2 layers now, so you may get the cover now from the distance from soffit to the center maybe at 90 millimeter, roughly speaking, I'm not exactly calculating, or maybe at 100 millimeter. It depends. We will discuss how much would be the clear gap between the layers, and then we will calculate based on first movement area principle where is the centroid. Actually, just suppose if it drops to out of 450, I subtract 100 millimeter as the cover, so it means I will be then left with 350 as effective depth over here. So it means now the same cross section with one more steel layer inside will have the reinforcement ratio. How much? 6 into 510 divided by 300 into 350. Good, 2.9. So it means now you will be somewhere over here, very close to row balanced. So obviously, when you will perform the capacity analysis, you will realize that your epsilon S will be very close to epsilon Y, little above epsilon Y, and your phi will not be now 0.9, it may be 0.67 or 0.68, depends on epsilon S. So in this way, assessment of row minimum, row max, row balance right in beginning, and then checking your cross-section row will help you a lot in classifying your cross-section. So I always recommend students to keep in mind these row equations because these are very useful expressions for classification purpose. In Viva, in interview, in quiz, such expressions can give you very quick assessments and you will be very confident in classifying your cross sections. Now, as I mentioned, last slide of this presentation, then I will take 5 minutes break, and then we can continue our next portion. This slide I have prepared by copying from latest publication of ACI 2019 in chapter 21. They have made a little modification in classification of the cross sections. So just for your information, now they are not asking you to have a cross section 0.003 and versus 0.005. So in this way, Now this strain diagram, as I have discussed with you based on the previous publications, that 0.003 versus 0.005, what they have now suggested, because in the current code they are allowing higher grade steel bars in the flexural members, 520 grade and above. So for that purpose, now what they are recommending, that for all steels, determine the strain, yield strain. For example, for 520 grade, first determine the yield strain. If it is 0.0026, add in that fixed 0.003, and then use that as the magnitude over here to classify the cross section, whether it is tension controlled or in the transition. For example, as I have given you example, that in the cross section, if you are using, suppose, 520 grade, so 520 over modulus of elasticity 200,000 megapascal will give you how much yield strain? 0.0026, suppose. So 0.0026 plus 0.003. So now latest code will ask you that use 0.0056 versus crushing to classify the tension control section. And in our example problem, what we have solved at the moment, it was grade 300. So grade 300 has yield strain 0.0015. So as per latest code, it means 0.0015 plus 0.003. So latest code will relax you that for grade 300 steel, even if your uh, steel strain is at 0.045, suppose, still you will qualify the tension control section. So rather than fixing 0.005, because in previous publications, the maximum steel grades normally in practice was 420 grade. So 0.002 plus 0.003 was quite safe to fix the strain value to 0.005. But now in the latest, you can say, working conditions, since higher grade steel bars are also in practice, so to accommodate them, now they are suggesting to calculate their yield strains, then plus add them in them 0.005, so that even for higher grades, we can also decide a safe magnitude of strain to ensure the ductility warning in the cross section. So this is a little amendment in the current publication. This is just for your information, but for your academic problems, considering examination point of view, you can still use 0.005, because all our derivations and assessments we are going to perform for the, you can say, the epsilon s equal to 0.005, and you will agree that mostly in practice, even in Pakistan and abroad, mostly 420 and below grades are practiced. So for them, answer is still 0.005. So still we are safe to use 0.005. But if suppose in a project you are using a higher grade steel bar, then be careful. As per latest guideline, you will determine the strain magnitude, that what is allowed. For example, for 520, now the threshold will increase from 0.005 to 0.056. So it is just one information. For compression control, no change. Only for transition and tension, they have now fixed a 0.003 plus whatever the epsilon y is, add that in the fixed 0.003 and get the target strain to classify your cross section. So at this stage, I will stop today's half portion recording of today's lecture, and then after 5 minutes break, I will continue presentation on the same topic. So if you have any questions, you are welcome. At the moment, 38 attendees are visible, so let me download. So if you have any questions, please welcome. This first hour lecture is being uploaded on files folder. Yeah, about a minute ago, this recording is now present. Before we start design problems, so few more important slides are which I want to discuss today, and then we can continue with the design of the cross sections. So after break, I will start from this slide onwards. So if you have any question, you can raise your hand, or you can open your mic and directly you can question me. This presentation, briefly I will discuss what you have already covered with allowable stress design topic. So in under reinforced failure, so this slide will actually so let me zoom in. Now, in under reinforced failure, there are various stages which are highlighted here. First is stage uncracked section. Neutral axis position is fixed, means internal lever arm remains constant because section is gross, it is uncracked. So what it means that your CC and T, their magnitude will get bigger and bigger, but LA remains constant. Only T and CC will increase with load. And section is uncracked, neutral axis is fixed. When cracking will take place, neutral axis will start moving towards the compression phase, means lever arm will increase, and also magnitude of forces are increasing. So as I said, when uncracked, T and C will get increase, but LA is fixed. Once cracking will start, movement of the neutral axis will start, and lever arm will get bigger, as well as increase in magnitude of the forces. More strain in the steel, so more stress. So if it has not touched yielding, so we can have more stress magnitude. If yielding occurred, then obviously T will become constant, because in USD we use ASFY. With further increase in the load, yielding in steel will occur. So it means now magnitude of force will become constant, and since T is ASFY and T is equal to C, so CC and T will become constant, and now only increase will be increase in the lever arm, because with the crack propagation up, lever arm will still get bigger. So LA here and LA in this case, in your ultimate condition, are different, but CC and T are now getting constant, because we are using ASFY as the maximum force which we can put on the steel bars. So failure initiates by yielding of the steel, but final failure is still by the crushing of the concrete. So this is important point, that our steel will keep on yielding and then strain hardening, and then until final fracturing of the steel bar will take place. Before that failure limit, concrete actually will burst, it will crush. So steel may be somewhere over here or here or here, but eventually what will happen, concrete will approach its crushing limit first. These are few stages which are to be kept in mind. Now, in order to design a cross section, design means that we have done one example problem in which we calculated the capacity of the cross section. What is the moment resistance that the maximum stressed cross section can resist? But if the same problem I reverse and I ask you to design a beam of span 5 meter for an ultimate load of 50 kilonewton per meter, then you need to determine the area of steel in the cross section. The problem is now first to select the size of the cross section, and to then calculate area of steel, and finally then sketch that steel will be in one layer, two layers, how many layers. So design problem means to calculate area of steel. Now, in order to calculate area of steel, we are going to derive a useful expression which will help us to determine the area of steel for design problems. And design moment capacity, you will agree that we have two equations since T is equal to Cc. So either we can use T into lever arm or C into lever arm. Our ultimate moment resistance with phi multiplied with the nominal capacity will remain the same. So phi into T into lever arm or phi into C into lever arm, answer will be same. But in this derivation of rho, I am using T into lever arm equation, and I am replacing T with ASFY and lever arm with D minus A by 2, and I am interested in tension controlled under reinforced cross section, a rho against that behavior. So I am replacing phi with 0.9, and in this way I can get equation 1 from movement equation, which is T into lever arm. In this first equation, uniform stress block depth A is present. If I replace this A with the A which I will determine from again a equilibrium equation, longitudinal equilibrium equation T equal to C, with the condition that at ultimate steel is at yield. So T is ASFY and C is 0.85 FC prime into AB. So from this basic equation, I got A value. Important is that in this A, steel yield at yield is used. So 5.9 tension controlled reinforced, and A also reflects that a cross section in which steel is at yield. So in this way, when I substitute A with this value, putting A in the equation 1, what I will get here, ASFY divided by 0.85 C prime B into 2. ASFY 0.5 C prime B into 2. What I will do again, I will replace this AS with rho BD, because AS over BD is equal to rho. So this will also be replaced here. Wherever AS is appearing, I am replacing AS with rho BD. And since it is the equation for movement resistance, I started from the internal capacity or movement resistance phi mn nominal multiply with the phi. In order to use it for design, I will equate this internal ultimate movement resistance with the demand mu, which, as I said, that if I ask you to design a beam for a load of 50 kilonewton per meter, and if it is the ultimate load, So you will calculate for that beam 50 into 5 square over 8, WL square by 8, MU. And that MU actually you will equate with the movement resistance, ultimate movement resistance. So what I am doing, I am comparing the demand with the ultimate resistance. So this equation can now be rearranged, as you will see that this D was present here and also over here. So this D is brought common outside. So since already D was present, so it became D square. Furthermore, this, when we brought D common outside, it will become 1 minus rho, since B over here and B over here has already cancelled and D has been taken outside. So we are left with rho into Fy divided by 2 into 0.85 into Fc prime. I will take this BD square as denominator on the left hand side. So it means now the right hand side is 0.9 into rho into Fy, and what is in the circular brackets, I am splitting this second component within circular brackets into two parts, rho by 2 into Fy over 0.85 Fc prime. So this is just rearrangement, nothing else. So this I will now be replacing with that this entire term mu over bd square, just to make my equation smart. This mu over bd square, I am replacing it with R. Since mu is kilonewton meter, B is or Newton millimeter, and B is in millimeter, D is again in millimeter square. So when I will put the units, finally answer I will get in terms of stress, and megapascal is being calculated here because I am putting, if I am putting mu in Newton millimeter and every dimension in millimeters, I will get the answer in Newton over millimeter square. Similarly, I am replacing this phi 0.85 C prime over Fy with omega. So this will help me to make my equation smart. So now it means this is R equal to 0.9 rho Fy, and then within circular brackets 1 minus rho over 2 into omega. Again, I will rearrange, and this Fy and 0.9 I brought as denominator on the left hand side, and the right hand side will be now rho into the term within circular brackets. I will again rearrange until I get a quadratic equation of rho. So this rho square and the denominator I can cross multiply and simplify. I will get a quadratic equation of rho. And when I have a quadratic equation, I will get two roots. So when I will get two roots, I am actually getting two roots of rho. So which out of them will give me a tension controlled under reinforced reinforcement ratio that is important. So this rho, this quadratic equation has been solved, and I am getting two roots plus minus. So you can do this by making such alterations to make the equation more smart. So what is done here, it is 2 omega into r over 0.9 Fy, and along with that they are multiplying the equation and dividing the third component with 0.85 C prime over 0.5 C prime. In this way, the Fy and 0.9 into 0.85 and 0.85 into 2. So actually this Fy and this 0.5 C prime, they actually converted this Fy also into omega. So then omega will become omega square. This is just one attempt to further make the equation more concise. And now with the for the determination of roots of the equation, you will get plus minus and then terms under the root divided by 2, because it is 2a and with a there is 1. So I will further simplify this by taking it common outside. It is present here, it is also present here. So when I take this common outside, I will get this shape of equation 1 plus minus square root of 1 minus r over 0.385 Fc prime, and we have to use, out of the two roots, we have to use the negative sign to determine that rho which will give us tension controlled under reinforced cross section. Because if I will select the positive root, I will get the rho even bigger than rho balanced, which is undesirable. For under reinforced design, I need rho to be less than rho balanced. And incidentally, one out of the root with plus in between is giving me the rho which is above rho balanced, and this has been proved here, because when it will be plus over here, it will become omega, and omega is already 0.5 C prime over Fy, which is in balanced reinforcement ratio equation, it is present. Then furthermore, once it will go inside, we will have in the balanced equation beta 1 600 over 600 plus Fy. So this term in balanced equation is less than 1. But here in our case, we will get the answer if I'm selecting plus over here, the answer above 1, because it is 1 minus this and under the root. So it is unacceptable that I will get the second root which is even above rho balanced. So I am using intelligently out of two routes the one which will give me the row either equal to row max or less than, because indirectly I am interested in getting a section which is under reinforced. So this is important derivation, and don't forget that we started from the interpolation. We substituted each and everything according to tension controlled under reinforced failure, A of our choice, phi of our choice, and we then compared the moment resistance with the demand, and after simplifying we got quadratic equation of rho, and out of them one root has been selected which will give me the rho definitely less than rho balanced, and in a way I will be in the domain which is desirable. So it is up to you whether you memorize this equation, or I can rewrite this equation in more expanded form. So it is up to you whether you want to memorize this one or the equation which I am going to rewrite for you. The same equation, I am going to expand it with the original terms. So rather than using the replacements, let me expand this. So it is actually 0.85 FC prime over Fy into 1 minus then square root of 1 minus 2 mu divided by phi b d square into 0.85 FC prime. So I normally use this equation rather than using this one, which has some, you can say, substitutions that you are putting R instead of mu or BD square, and here it is 0.5 C prime Fy. The original equation is this one. So it is up to you which one you want to keep in mind, but the important thing is, since it will be used for design problems, as I said, that design a beam for suppose ultimate load of 50 kilonewton per meter. If this is the question, using ultimate stand design, beam span is 5 meter. So if this is the direct question asked, what you will do, since beam is simply supported, so the maximum moment demand will be at mid span, so you will determine WUL square by 8, 50 into 5 square over 8. that mu you will put over here. Then comes the decision that in your beam, which FC prime and Fy you are going to select. That also depends on the nature of the project. Is it a low cost project, low rise, private or public sector? So normally for low cost projects, you will select FC prime 20, and Fy now in Pakistan is typically used of grade 420. So it will be your choice to select FC prime and Fy if not given in the statement. And then if you will notice that actually you are using this equation to determine rho, and you know that this rho will guarantee you tension controlled under reinforced failure, which is desirable one, and if you have the rho, you will multiply this with BD to get area of steel in the cross section. So as a design problem, if you are only provided with the beam span and ultimate load at least, that's it. It is your duty to determine maximum moment demand, decide FC prime over Fy, decide width of the cross section and the gross depths. Obviously, in selection of the B and H, architectural considerations as well as serviceability requirements, that serviceability will dictate you that your H should not be less than this limit. And I have shared with you one table of ACI based on end conditions and steel grade. H was proposed for simply spotted, and if grade is 420, recommendation of H is given. So your H should not be less than that to control the deflections. So after selecting the cross section, you will also be assuming at this stage that you will end up with how much steel layers and what will be the comfortable cover which will fulfill all the code requirements, so that the resultant effective depth which you will estimate will be used here. And moreover, phi, definitely you will use 0.9 because you are actually determining that reinforcement ratio which will give you tension control under reinforced failure. All this you have to done. You have to select in design problem, starting from material strengths to cross section selection. And once all these decisions are rightly made, you will get the rho value. Just for sake of practice, at the moment I have not given you too much information that how you will select D, effective depth, or gross H. But just at this stage, if I ask you that Let's apply this equation on our example problem that I am telling you that a beam of span 5 meter has the ultimate load 50 and it has the ultimate moment at midspan. How much? Can you tell me? Ji, please.
Sir, 156.25 kilonewton meter.
कितने हैं जी?
156.25.
जी 50
156.
नहीं, मैं दोबारा मुझे बताएं. 50 into 5 square divided by 8 ऐसे निकाला है आपने? आप
Yes,
कह
sir.
रहे हो 150 point
156.25.
156.25. Agreed? So just for this practice problem, if I select, I will talk about this selection of B and H in detail. If at this stage, based on your previous experience, you know that H 18 inches and then cover of 3 inches 75 millimeter and resultantly effective depth 375, you already have evaluated while doing capacity analysis. So based on my previous recent experience, let me select for this beam H450 and D375, assuming cover of 75. And based on my previous experience, let me select FC prime 20 and FY 300. And let's find out what is the rho from this equation, which I am using now for design purpose. Don't forget this mu over here, you will use in Newton millimeter. So you got 156.25. Multiply this with 10 raised to the power 6 to convert it into Newton millimeter. Then multiply with 2. Actually, I'm expanding this equation and I'm rewriting it here. So you will get the same answer into 2. 5 you will put 0.9. B, in our recent problem what we have solved, we selected B 300. Normally this B will be controlled by the support dimension. What is the column size, and that normally will govern. Moreover, the available formwork plate sizes. So we start from 228 millimeter, normally 9 inch, because in some cases we want to conceal the beam within the wall. We want no offset above the wall. But if beam is wider than the wall, there will be offset. If I want to conceal it just above the 9-inch thick wall, then I may prefer D equal to 228 millimeter, but 9 inch. But in some cases, if I want to accommodate more steel in one layer, I may be preferring more wider width. So 1 foot 300 millimeter, and beam, if it is resting on a column and column size is 300, then 300 beam, 300 column will flush. There will not be any offset. So normally starting from 228, 300, 375, so multiple of 3 inch commonly used in Pakistan, 9 inch, 12 inch, 15 inch, 18 inch, 21 inch, 24 inch. So multiple of 75 you can say millimeter. In this problem, I am using the same 300, and D from my previous solved problem, I am using 375 with scale. then 0.85 FC prime 20. So can you tell me what is the rho? In order to apply this equation, you can write simple programs, or on Excel you can write this equation so that quickly once you put FC prime and Fy and B and D, you get rho value quickly. So this equation you are going to use repeatedly for design purpose. Again, I recommend you to memorize this equation because this will remain part and parcel of you if you are to become a designer. In reinforced concrete design, this is the design rho, and this rho expression you are going to use to design tension controlled under reinforced cross sections. So first tell me 2 mu over 5 BD square into 0.8 FC prime. What is the answer of this? Convert movement to Newton millimeter by multiplying kilonewton meter with 10 to the power 6. Then whatever is the result, subtract it from 1, take square root of it, then again subtract it from 1, and then multiply it with 0.5 C prime over Fy. मुझे अभी तक एक ही स्टूडेंट मोस्ट प्रोबेबली कैलकुलेशन करके बता रहा है, बाकी जो है वो एक ही पर तवक्कल करके बैठे हैं या अपना भी कोई कैलकुलेटर आपके हाथ में?
सर 1.6% आता है राव।
ये इसको मुझे आपने परसेंटेज में नहीं बताना, जस्ट टेल मी इन रेशियो विदाउट परसेंट.
0.0159.
Sure? Anyone
Yes.
else got the same answer? 0.0159. Agreed? Now, if I am confident that I have not made any mistake in calculating this reinforcement ratio, it is very close to 1.6%, right? And just few seconds ago, well, not few seconds, few minutes ago, we estimated the rho max of the cross section with the material grades 20 and 300, and you mentioned rho max 1.8%. So it comes out to be 1.59%. So I'm happy that what I have calculated the rho is less than rho max. And obviously it is greater than rho minimum, because rho minimum you have estimated few minutes ago, it was 0.4, 0.45 or 0.46 for the material grades which we are using in this problem. So our rho 1.59% is less than rho max and greater than rho minimum. So our selection of 5.9 is valid, and if I multiply this rho with BD, I can get area of steel. So area of steel is 0.0159 into B 300 into D 375. So how much area steel you will get in millimeter square? For your example problem,
1788.75 millimeter square.
17
28.75.
1728.75
No, sir,
millimeters.
1788.
जी दोबारा बता दें।
1788.75.
आपके ना बैकग्राउंड में बड़ा नॉइज है या डिस्टरबेंस है?
नो सर, वो किसी और का माइक ओपन है।
जी बिल्कुल, आप दोबारा बताओ, शायद आप मुझे क्लियर हो जाए।
1788.75.
गुड, 1788। .75 millimeter square. Now this is the stage where I want to consult the design aid. Since you have seen that I have, please mute your mics. Since I have seen that I have mentioned in my previous lecture that there are design aids, and in ACI code the table is available in appendix B. So various bar sizes and their nominal areas are summarized. Now if I select 3 number 25 bars, so 3 into 25 bar nominal area is 510, we get the answer 0, 3, 15, 30. Less than. The reason is, now I have given you a load 50 because in our example problem the load was less than 50. I increase the load, so is my demand of steel. So if you are designing against 45 or 46 or 40 kilonewton per meter, you probably will get the area exactly equal to what we have analyzed the capacity of a beam of 5 meter span, and we got the ultimate load of that beam. Here I rounded up the demand, so is area steel is not 3 number 25 bars. If I will put 3 number 25 bars, I am designing under designing the cross section, unacceptable. If I select 4 number 25 bars, 4 into 510, so 4, so I am doing over estimation against 1788. I am getting 2040. So this much round up is not also desirable. If I select 2 number 25 plus 2 number 19, then 2 number 25 means 2 into 510, and 2 number 19 means 2 into nominal area of number 19 is 284. How much answer I will get?
1588
जी कितना जी?
सर 1588
जी फिर आवाज में इको है दोबारा.
1588
नॉट क्लियर येट. फिर बोलें. It is
1588
1588. Okay, okay. So not yet. You can say acceptable. It is less than 1788. If I will select two number 25 and two number 22. So number 22 nominal area, you can consult from the design aid that how much is the nominal area of from ACI against 22. If you will consult the table, you will get area 387. 387. So 2 into 510 plus 2 into 387, how much?
1794
1784. So theoretically speaking,
94
please दोबारा repeat करें.
1794
1784. So theoretically it is still few millimeters less than the demand. So theoretically it is not yet right
No sir,
selection.
it's 94 not 84 1794
आपकी ना आवाज में काफी इको है. आप इस तरह कह दें कि अबव है रिक्वायरमेंट से.
सर 1794
yes sir above
Okay,
requirement से
good, very good. Then it means our design is final then. So I can sketch it like this in 500 in 300 millimeter width. I can safely put 4 bars without any problem because in that width I can accommodate 4 bars even after fulfilling the code requirements of clear gaps between the bars and edge covers. So final design will be then 4 bars, 2 of size 25 and 2 of size 22. So this is just one practice example just to give you idea that how useful this expression will be to quickly design your beams and you are getting a ductile beam fulfilling all the requirements. Without any doubt, if you will calculate the row of this beam, your row will be less than row max, it will be greater than row minimum. So it is a tension controlled under reinforced design. So in next lecture, we will continue from this discussion onward. So let me end the show and stop recording of today's lecture. So this video will also be uploaded. So I have 1 hour class with section A, I think. So if you want to join, you are welcome. But if you have other class, then you can quit today's meeting. I will upload PDF of today's presentation as well. So do you want to say something? Mohsen Rana? Mia Hassan? If no, then okay. Allah Hafiz.